is Colquim. Hope everyone knows who he is, but we have some new faces, so I'll just do a quick introduction. So Suzuki is one of the research fellows here. He got his PhD in 2000 from Soken Dai, Japan, and then he did a postdoc in CFA, and then a postdoc here, and then he promoted to faculty here at ASIAA since 2003 or 5. Okay. Anyway, so Suzuki is one of the leaders of the GLT project, one of the major projects at ASIAA. I'm sure you've all seen the black hole images. Suzuki is one of the people behind it. So he's going to tell us more about the GLT project. So let's welcome the speaker.
Thank you. I'm not sure whether any people know me, but because if there's no COVID-19, half of my time is away from Taiwan, mostly in Greenland. So, but this time I'm completely stuck in Taiwan. So now I have a chance to talk in front of people. Okay, so today I'll talk about GLT, past, present, and future, because I think many of the summer students and some of the new postdocs, faculties. So originally I was just talking about the current status, but now new people is here. So I will talk about the really past, how it started, and what's going on, and what we are thinking about. Okay, so the primary science target for the GLT is that direct imaging of shadow black holes. Before last year, April 10, how black hole looks like was, the famous one was this movie, Interstellar, that Kip Thorne, the Nobel Prize winner, calculated all those black holes, and this was what it looks like, expected. But now, after April 10 last year, we know black holes look like this. And unfortunately, GLT was not involved in this imaging, but of course, we helped a lot for the JCMT. It belongs to East Asia Observatory, and we started up all those instruments for the EAO after JCMT moved to the EAO, and help out the observation for the JCMT, calculation, data reduction, imaging, theory, everything we helped as a part of the EHT collaboration, Event Horizon Telescope collaboration, and we got this image. So, because of this image, now we know that M87, the shadow size of 42 microarcsecond, mass of 6.5 billion solar mass, with the distance, this is assumption, 16.8 milliparsec. Now we know that. And think about the spatial resolution. The spatial resolution goes down with spatial resolution goes high with shorter wavelengths or higher frequency and bigger telescope or long baseline. So resolution is proportional to the wavelengths over diameter of the telescope or baseline. And think about the spatial resolution of the optical infrared telescopes. Now it's available. HST, Hubble Space Telescope, equals to the 0.004 arcsecond, which is 40 milliarcsecond. The future project, James Webb Telescope, Space Telescope, JWST, 0.03 arcsecond, or 30 milliarcsecond. And current highest resolution optical infrared interferometer is a VLTI, Very Large Telescope Interferometer. It goes to the 0.002 arcsecond, which is 2 milliarcsecond. By the way, for the ALMA, it goes to the 0.01 arcsecond. This is the actually, this is not yet for the observers, but this one is currently tested at the ALMA high frequency long baseline test. Probably I will give a talk at the ALMA meeting at the 2 weeks later or something. But yeah, current technology goes up to 10 milliarcsecond with the ALMA, with the testing mode. So again, I said that the black hole size is microarcsecond, so that the 1,000 times still, this is far, far away large, so that we cannot image we cannot see with those kind of instruments. The only things we can do is the submillimeter very long baseline interferometry. That's the only technology currently we have to really image the black hole. Then, why Greenland? When we started the Greenland Telescope project, well, actually, at that time, we were not sure where to put the telescope. And we, especially Keiichi Asada, did the site selection criteria. First, precipitable water vapor is low. Well, low water vapor because submillimeter wave is absorbed by the water vapor in the atmosphere of Earth, so that we have to avoid that. The longest possible baseline was the existing submillimeter telescope. So for the VLBI, there's no point to put the telescope where the telescope already. Then the short baseline is too short, zero baseline, so that we have to find that site with no existing submillimeter telescopes. So that the telescope, submillimeter telescope at that time is these telescopes: Hawaii, Arizona, Spain, Mexico, Chile, South Pole. So we have to find out somewhere not these kind of sites. And overlapping sky coverage with ALMA, because the ALMA has the largest aperture size. There's a 66 12-meter telescopes with the so that the correspond to 85-meter single-dish telescope for the aperture size. And the key point is interferometric baseline sensitivity. It goes with the aperture size of one antenna to the aperture size of the other antenna. This and square root is the sensitivity. So if you have the interferometry with ALMA, even you have the small telescope, ALMA has a huge sensitivity, so that we can have the really good interferometry baseline sensitivity, so that we have to observable together with ALMA. That's the key point. And also accessible. That's also another thing. So Keiichi looked for the NASA satellite data. The red part is that the PWV water vapor is too high, and purple is that the water vapor is low. So we have to find out and this is the winter in the north, summer in the south, opposite. Winter in the south, summer is north. And around here, as you can see, completely red, so that around here there's no good site. Australia, Africa, Asian countries, nope. There are some good sites in South Alaska, but this is Mount Denali. It is very difficult to access, so no. Tibet, actually this is the best East Asian site. But unfortunately, it is exact opposite of the ALMA, so that we cannot have the baseline with ALMA. So this is also not good. The only place we found out is the Greenland, which is even summertime, it's pretty low, blue, and exact north of the ALMA, so we can have the baseline with ALMA. And also SMBH, which is also another telescopes that Taiwan is operating. So that the Greenland looks pretty good. And actually, that if you Greenland, so that you're here, so that compared to the available telescope, baseline lengths expand more than 9,000 kilometers, so that it will, if you see this UV coverage, red part is the GLT related, so that all the north-south baseline, where there's no baseline currently, can cover with the GLT baselines. So this is the reason why we choose the GLT, our telescope put into the Greenland. The EHT 2017, this image, actually, if you consider pixel size, it's only 3 by 3 pixel, because the resolution, this whole is compared to the one resolution for the EHT 2017. So this map, actually only 3 by 3 pixel image, pretty bad image, actually. But unfortunately, this black hole size was exactly the size of the current resolution. We could see the hole. If black hole mass is half the size, we couldn't see it. EHT was GLT. Actually, EHT 2018, GLT joined the the observation, and we are expecting we will have the 5x5 pixel map with the GLT, so that EHT 2018 data, hopefully we can have a better resolution. By the way, background is the simulation map, which made by Keiichi and others. So this is just hopefully looks like this. So this is why we decided to put the telescope at Greenland. So telescope reassembly at Thule. GLT antenna is actually the ALMA North America prototype 12-meter antenna made by Vertex. And NSF, National Science Foundation of the US, awarded to ASIAA and SLT in 2011, so that we did antenna performance inspection in 2011-2012, and looks like it's working pretty good. So 2012, December, that's the, by the way, actually it was located at the VLA site in support, New Mexico. And we disassembled and clean up, completely clean up. And we did upgrades for the, especially for the moving part, gears, because the weather condition at the ALMA site and the Greenland is completely different, especially for the temperature. ALMA site only go down to probably 0 degree or -5 degree or so, but the Greenland go down to -70 degree, so that we have to install the gears or moving parts that can survive even the -70 degree Celsius. So we upgraded, and 2016 March.
How could we make sure under such a low temperature is working?
Oh, that the ARC, they have the cold chamber.
I see.
So that the
also
also
way to such a low temperature.
some those kind of tests has been done. Yes. And the 2016 March, we reassemble partially at the North Fork, because this is the port to go to all the way to Thule. This is Thule, and the ship container just arrived at the July 2016 from Norfolk. And for the 2016, before the winter comes, we constructed like this for the lower part and dish part at the inside the container like this. Then, because wintertime it's too cold to work at, well, especially Tashi have to work in the cold winter, so that the wintertime it's too cold to work, so that we stop at here. And again, next year, May, we started to install the dish surface to all and measure the surface accuracy. Bring the whole dish from the container to the telescope site, put it on, and 2017 July 24, we finished the antenna construction at Thule. By the way, this is a Google map of Thule. This is a US Airforce Base in Greenland, Thule, located here. It's made at the 1953. It's a Cold War era, because it is very close, one of the closest to the, at that time, Soviet Union from the US. So US and Denmark secretly made this US Air Force Base. Although now you can see in the Google map, it's not that a secret. And telescope site here. Before 2016 summer, there was nothing. After 2016 summer, you can see that some construction is ongoing. Actually, this is the pad for the telescope, and many antenna components are located like this. And recent Google map looks like this. Actually, telescope's here. If you zoom it, yes, you can see the telescope is here. Probably looking at the genus. So, well, if you have a chance, take a look at the Google map. cannot see nobody. I cannot see someone working. So, commissioning and science operation, first year, 2017 to 2018. So Greenland Telescope looks like this now. This is taken by Mita, nice picture. And receiver, inside the telescope receiver is like this. Actually, we have the 300 receiver, 86 gigahertz, 230 gigahertz, and 345 gigahertz. Mainly made by Johnson and Ted here. And, well, 86 gigahertz receiver, everything in 1 pixel. It's using the rebuild of the Amoeba project receiver, so that thanks to Amoeba for this. And 230, it is Osaka Prefecture University custom receiver, this one. And 345, actually we're using exactly the ALMA Band 7 receiver. So, as I said, at the 2017, actually November, the receiver has been installed and given to the astronomers in December 1st, 2017, actually. And within the month, we got the first light with the scanning the moon actually at the Christmas Day. With Kevin and me, I was at the site, and yeah, so that the succeeded for the astronomical first light for the GLT. It was within 1 month. Within 1 month that the telescope was ready, and 2 weeks later we detected the CO line with the CO221 line, with using the toward the Orion. Actually, it's very low because Orion is southern source, and well, KG, Shoko, Kevin, and me, I was at the site, detected, and within 2 months we joined the EHT 230 gigahertz VLBI dress rehearsal. At that time, ALMA and South Pole Telescope was joined, and JSMT and Iran could not join due to bad weather. And we observed 3C279, and this module quickly discharged to the MIT haystack. And meantime, image from the SAO, Kwan Yu, Keiichi, and Hiraki at that time. And actually, we got fringe. And well, this is the pretty difficult to see, but you can see the red is the phase. You can see the phases concentrated on around the plus minus 180 degree, and signal detected here, so that the within 2 months after telescope has been construction finished, we detected fringe. Probably this is the world fastest ever to detect such kind of high frequency fringe with the VLBI system. Actually, this is with ALMA, so that 9,000 kilometers away from the GLT. So that well, we can say that our engineering and science group of the GLT team is really, really good. So EHT 2018, we did with this kind of telescope, and GLT joined. Actually, at that time, those kind of telescope joined, and well, especially again, Keiichi, Nimesh, Hiraki, and Chenyo was at the site and helped for the EHT observation. I was at the JSMT. And also, after this, we also started to join the GMVA, and that's a Global Millimeter VLBI Array, another VLBI network at the frequency of 86 gigahertz. And this one also detected for the first time, pretty good. So this finished the first year's operation. Second year, 2018 to 2019, the key was that the surface improvement by the photogrammetry. This photogrammetry method is to put the target, reflective target, onto the surface dish, taking a lot of pictures, and calculate the separation of the those kind of the target, and calculate the surface accuracy of the telescope. And this was the first map we obtained. Actually, it was 180 micron. It was pretty bad, very bad. and we surprised. And detailed discussion within the engineers, especially Philippe, Ted, and so on, Mita, and so on, and find out that those kind of red part is the pickup point when we install the dish onto the receiver cabin. So that this kind of rope was at this red part. And obviously, because we did that, the dish was deformed like this. So after a lot of photogrammetry and dish adjustment, especially thanks to Ted, Philippe, Tashin, and Joshua, worked a lot and reached to the 21 micron after that. Completely beautiful, not like these kind of things. And then, because of the surface improved a lot, we now could do the 345 gears observation and detected the first light with a 345 toward the moon. Very bad signal to noise ratio, but opacity, 200 gears opacity was 0.5 and elevation was 13 degrees. So, well, of course, not bad, but good. We detected with 345 gears receiver. And after rough focusing, we detected the CO322 line toward the IRC plus 10 to 16. And more focusing, more pointing model. Then we started to detect like 813 CN or SO or those kind of weak lines too. So after the surface improvement, now we could do all the pointing by the astronomical lines for the 86 gigahertz SIO2219 line, 230 gigahertz CO221 line, 345 CO322 line, with the whole sky pointing with those lines. And now all the receiver reach to the pointing accuracy constantly 3 arc second or lower. So the pointing is pretty good now.
So you don't know the elevation dependence of the surface yet?
No, that the problem is that we couldn't see planets in winter time. So that it's very difficult to do the elevation.
Because it's too low? Well, why can't I see that?
No, that too weak.
Too weak.
Yes, that to have the such kind of focus curve, they have to be very strong. But currently we haven't done that. Yes. Okay, third year. Aperture efficiency increased. Originally, when before the EHT 2018 run, because of the surface was really bad, so that the efficiency was only 20%. But 2019, January, it goes up to 35% after the photogrammetry. And just before I came back running away from the COVID-19 from the Thule, it reached to the 65%, correspond to the 40 micron surface accuracy.
At 230?
230, yes, 230. Everything is 230, yes. The thing is that the photogrammetry is done at the summertime. Well, actually this was summertime, and this was done in the fall. And of course, telescope structure is depending on the temperature, so that in fall it reached to 20 micron, and in winter time the calculation suggests that it will degrade to 40 micron, around 40 to 50 micron, and it was well correspond to that number. So we think we are doing okay. Another thing, last year, is that the GLT backup receiver has been installed to the JCMT. Now it's called Namakanui for the JCMT. It is exactly the same copy of the GLT receiver. And if something happened in the GLT side, this will be moved out and sent out to the Greenland. And because it's within the US, it's much easier sending from rather than sending from the here, like custom or those kind of things. Doesn't affect by the those kind of things. So, and now they detected the first light with the total CO221, so they are also working fine. So this year, February, we performed the East Asian 230 GHz VLBI test observation with the GSMT, GLT, and SRO. This is the Seoul Radio Astronomy Observatory in Seoul, Korea, with 3 antennas. And data reduction is done at the Shanghai Astronomical Observatory in China. So it's completely East Asian VLBI network. And actually, we detected the first fringe only by East Asian collaborations. So that the now we can do the this kind of observation with the only with the East Asia. Of course, baseline length is baseline number is not much, but such kind of currently EHT observation only happen once in a year. Well, okay, this year didn't happen because COVID-19, but yes, if we want to do some monitoring observation with those kind of with the East Asian antennas, we can do such kind of brief monitoring observation. Now, so far, GLT VLBI success rate is 82%. 9 out of 11 observation has been succeeded. So this is pretty good successful rate because VLBI is very difficult. When you're observing, you are not sure really it's okay, but now, so far, it's doing very good. So these are the current status of the GLT. So a little bit shift to the something interesting side. Life in Thule. Work. Sometimes you have to work at minus 40 degrees outside temperature. It was really cold. My lowest temperature experience at the site. And you have to wipe the dish to take out the snow because it's snow a lot. And after 10 minutes, you'll be like this. By the way, this is Nimesh Patel from Smithsonian. I took the picture. Yes. So this is what the work means in Greenland. But occasionally, I don't know whether this works or not. Winter storm coming suddenly. So we have to escape as soon as possible from the telescope site to the our condo.
How far?
About 5 minutes drive. Yeah, it's close. But next day, how it looks like is this like this. This is a control room container, and completely blocked by the snow. So everybody should have to show up and clean up, like all the container. Like this kind, the mechanical container, many containers are there, and we have to dig. Yeah, this is work life in Greenland. Not always.
Is that summer?
Huh?
Is that summer?
No, it's winter, of course, winter. No, summer is much better. Yes.
How is the ice?
Huh?
Icy, telescope or whatever, or even container could be blocked by the ice.
Oh yeah. Actually, this time I didn't show. Good point. I didn't show, but if fog roll around in the wintertime, the rime ice cover all the metal part. But actually, I didn't put it. This year we installed the de-ice system.
Okay, indeed.
And now that it works pretty good. Yes. Then at least for the surface,
right.
Dish surface, the de-ice will take out all the ice. Yes. That we confirmed. Yes. Daily life. Food is look like this. If you go to the buffet, there's one buffet, and you can choose whatever you want. And I don't want to eat meat, so that mainly I picked up fish. This is salmon and vegetables. I think this is locutus, and picked up the he loves meat, so meat. And breakfast, lunch, dinner, breakfast, lunch, dinner, same place.
Is it 24 hours?
No, no. Only breakfast few hours, lunchtime few hours, dinner few hours. So you have to go exact time to have it.
What's the taste?
It's US.
So US taste. Okay.
But some fish is actually Danish side because
okay.
Greenland belongs to Denmark, and many engineers works that the Danish people working. So that lunchtime there's a Denmark side, but the dinner pretty much US side.
Danish is better than the US.
Oh, for me, yes, because there's fish. There's a bar. I'm happy with that. Well, this is a US Air Force Base, so they put whatever the soldier needs. That's why it's so expensive, okay? That's why US military is so expensive. And go to there's a shop at the supermarket, and full of beer. I'm happy with that. If you don't know this beer name, it is very good craft beer from the US, so I'm very happy. And actually, we live in usually live in the NSF Dome. National Science Foundation has the one building, and occasionally we have dinner at there. And this is kitchen dining part of the NSF Dome. In NSF Dome, there's a kitchen, so you have to cook by yourself if you want to eat. So that me, Derek, Nimesh, Philippe is there, and Nimesh is a very good cook for the Indian food, and I'm happy. And Keiichi Asada is probably the best cook in our institute. I'm the worst of the institute. So if you have chance to go to the Thule with Keiichi, you'll be very happy. You can have occasionally you can have really good food. But me, if you go with me, cook by yourself or go to buffet. And occasionally we can have the barbecue like this. I think this is autumn, with several other people. Yeah. At the there's some cabin near the base. So if we rent there, we can do the barbecue. Nature. Yes, there's the iceberg. No, not iceberg.
Glacier.
Glacier. Yes, glacier background. So that occasionally the ice reach to the seashore. This is a field. And this is the edge of the Greenland ice sheet and land. This side is land. Above here, it's a Greenland ice sheet, which covers most of the area of the Greenland. And this is exactly at the edge. Occasionally, you can see the mirage that it looks like it's floating because of the air temperature difference. Rabbit. It's a lot, actually. It looks like big, but I heard that they're mostly very thin, but the fluffy.
Wild.
Can you eat them?
I haven't tried. Actually, they move pretty fast, so almost impossible to catch it.
So they are wild.
Of course, it's wild. Fox. Wild. Muskox, wild. And occasionally you have to go to patrol with the tauntaun. For the young people, this is Star Wars, okay? It's not real. But crazy Taos 2 people put my face onto the Luke Skywalker, yes. And occasionally we have the VSB visit to the telescope because the US Air Force Base, not much things to show. So Neil deGrasse Tyson came to the telescope. I'm not sure how many people know him, but in US it calls Carl Sagan 21st century, and they have a lot of TV program, and he came to take his TV program to our telescope site and also to the air base. Me and Kevin was there. The Prime Minister of Denmark came visit to our site. He's the guy, the previous one, not the recent lady one, but the first was the SP came to our site, and don't call his name. Please say Mr. Prime Minister. That was the warning. That's the only warning the SP told us. Barbara Barrett, I'm not sure how many people know, but this is Secretary of US Air Force, really the top of the US Air Force. But more importantly, she's a Smithsonian Institution board member, so she knows a lot of high-level astronomers, so I asked her to put money on GLT, but never happened so far. But I tried. And Nikolai Costa-Waldau, not sure how many people know, but Jaime Lannister of Game of Thrones. The only time I was not there. I wanted to be there. And Johnson and Tashin, they never see the Game of Thrones. That was my sad part of it. But, well, the reason is that he comes to take the documentary film, and actually his wife is the Greenlandic lady. Probably that's why. And we also invited the former Minister of Science Technology in Taiwan to visit Yang Hongdun. But this was cancelled due to the COVID-19. Too bad. But we will push again to those kind of Taiwanese VIPs come to our site. So that was the one part of the GLT. Then the last part, future plan, heading to the summit. Why Greenland Summit? Greenland Summit, located here, it is actually that there's a summit station operated by the US NSF and the Greenland government, started from 1989. It is mostly atmospheric and weather researches ongoing here. Altitude is 3,200 meters. It looks like this. And this is C-130. And, we fly with the C-130, and we can go through the land. In summertime, 45 people. Wintertime, 5 people. So we put the 225 years opacity radiometer in Greenland Summit. Thanks to Pierre and Keiichi, did a good job. So we operate for the 3.5 years. And looks like this is opacity data, and usually that the winter time, that here is pretty good, and the calculated opacity window for the radio from the 0 to the 1,600 gigahertz looks like this. So winter time, the 600 and 800 gigahertz window will show up roughly for 50% of the time. Terahertz is very difficult, but not impossible. About 10% of the time, it's possible in wintertime. Compared to Thule is about 2 or 3 times worse than the Summit, which means that what we can do in observation, 10 hours observation at the Summit, we need 100 hours at Thule, but only for the low frequency. High frequency, we cannot. So 10 times better at the Summit. That's the key point. And also the submillimeter. So if we go to the Summit, we can do the VLBI with 600 gigahertz, with GLT, SMA, JSMT, ALMA, all our telescopes, Taiwanese telescope.
SMA has no 600 right now.
Well, yes, but it is possible if we want, yes. But the thing is that the possible, that's the, yes. Of course, currently GLT doesn't have the 600 gigahertz receiver, so. So, go back to the size of black hole. If we go to the 600 gigahertz, the resolution reaches to 10 micron. Then the source number increases. M31, M60, those kind of things can be observed. So I told you before that the EHT 2017 was 3 by 3 pixel. If we include EHT 2018, it will be 5 by 5. But if we go to the 600 gigahertz, it will be 15 by 15. Pixel number 225. So one digit, 2 digit, and 3 digit. this is the improvement we can expect with the GLT, with the 600 gigahertz at the Summit. And this one, I simulated, I make the black hole size lower. This size corresponds to the M31 black hole size. So the M31 black hole, we can also observable with the 600 gigahertz. Of course, the flux is a different story. We have to measure how strong it is. But the key is that now we can only have one black hole, and in the near future we may have two, because the Sagittarius star may be coming. I cannot say. But if we go to the future, the Summit, the number of the black hole we can observe will increase, and now we can do the statistic of those kind of study. That's the most important part. Also, GLT can be used as a single dish, because VLBI can be done limited time. So most of the time we can use that as a single dish. So if we, I show that this is the Summit opacity, well, transmission, so that the terahertz, 10% of the winter time, it is possible. And Greenland Summit is actually based on my paper that the stable opacity stability is the best compared to the ALMA or even the South Pole. Greenland is most stable in terms of long time at lower opacity, so that it is very good for the continuum camera, and also time-consuming survey observation, like the big survey, and also monitoring. This kind of thing we can do with the GLT. So what currently we're doing is that we're pushing the collaboration with Denmark, because Greenland belongs to Denmark. We're studying collaborating with Danish researchers, astronomers. They have a lot of experience in single-dish science, both line and continuum science. And also cold environmental researchers. They are operating ice core, the ice drilling project. And they have a lot of knowledge, experience, and heavy equipment at cold environment. So that with help of Danish researchers, we can speed up our plans a lot, and we'll save millions of US dollars for the Summit development and operation due to the manpower, experience, and equipment. If we do it by ourselves, we have to purchase a lot of things, which is very expensive. But collaboration with the Denmark researchers, we can save those kind of money. And they have a lot of experience. And currently, for the astronomer side, we're talking with Thomas Grieve from the Tech University of Denmark, Jas Jorgensen, Niels Bohr Institute. I think Thomas came to Taiwan several times, so many of the exergat astronomers knows. Jas Jorgensen, he does the astrochemistry, so probably some of people knows the SMA. He was the SM postdoc in the past, and currently faculty at the Niels Bohr Institute, so that he's very good at astrochemistry toward the star-forming region. And Marianne Westart, Niels Bohr Institute, she was Kevin's former supervisor and doing the AGN study, so that we're talking with them. And currently we're pushing to install a continuum camera gizmo on the GLT. Currently we are calculating for those kind of optics and how to install it. And letter of intent has been signed on March 27, 2019. And now discussing to have a letter of agreement. Then we can have the collaboration. Then in the future, hopefully 2021, we finish to the operation, bring to the telescope to the go through the ice sheet with these kind of things, and hopefully 2022 or 2023 we can have the first light at the Summit station. So summary is that our GLT is that the primary target is that the direct imaging of shadow black hole with submillimeter VLBI. Telescope finish at Thule Greenland, testing and science operation at Thule is ongoing. And the surface library includes 25 micron. Oh, this one I didn't talk much. Plan to move 21, 22. And hopefully at science can be done at the summit on 22 or 23. So thank you very much.